Alright, so let's start working our way through exam 2 for the summer semester for Organic 1. So the question is asked, which of the following compounds contain chiral centers? All right, remember with the chiral center, you're just looking for a carbon that is bound to 4 unique things, and the thing to remember is that, hydrogen, right? We can count hydrogen as a unique thing, right? So if we have one hydrogen and then three other groups coming off of that same carbon, then that would be a chiral center there. Whoops, didn't mean to make it. There we go. Right. So I'm looking at these carbons right there. You can see they all have, we have a chlorine, we have a hydrogen, right? We've got a methyl group over here, and then we've got that propyl group over there, right? So this is a chiral center. Let me just clean that up, right? So that's a chiral center. Here, we've got the chlorine, we've got a hydrogen, that's unique, but here we have an ethyl group, and there we have another ethyl group. Right, so those are identical, so that is not a chiral center. Chlorine check, hydrogen check, a vinyl group over here, ethyl group over there. Those are independent, separate, unique, whatever you want to say, right? So that's a chiral carbon. And this carbon right here, right, that carbon right there is also going to be chiral, right? So all three of those are going to be, they have chiral centers. Okay, so pick one of these molecules and draw the enantiomers. We can approach this any way you really want. Let's just look at the one in green. So 1, 2, 3, 4. We've got a pentane. We'll draw one wedge and one dash, right? And then we will just swap the wedge and dash, right? That's all you got to do to draw the enantiomer, right? You keep two things the same and you just swap the wedge and the dash, right? So here we have the R version, and here you will have the S version. Not that you have to put R and S, but I'm just, just for emphasis sake, right? So, all right, let's take a look at this one here, right? Let's put dashed with the hydrogen, wedge with the chlorine, right? There's one. Right, now we'll dash the chlorine and put the hydrogen wedge, and there's the other, right? So there are your sets of enantiomers, right? And you could do the same thing with the last one also, right? So when drawing an enantiomer, just, keep two things the same, wedge, swap your wedge and dash or whatever you want to, okay? Cool. So I'm not going to read this whole thing out. You guys can follow along, right? Basically what this is, or pause and read along. Basically what this is saying is when you do a reaction with HCl, you add an H, you leave behind a positive charge, and then the chlorine adds where the most stable positive charge is, okay? And so then it says, okay, well, why would we expect to see this molecule at a higher yield as compared to this molecule over here? And so what I was getting you guys to take a look at is after we go through, right? After we go through and do this, right, we will end up with either this. Let me just make this a little bit clearer here. We will either end up with this or this. Okay? So why would this one be formed in a higher yield? Well, there's a simple answer for this. All I was looking for is some argument about being a resonance stabilized carbocation, right? Being a resonance stabilized carbocation. Here we can't really stabilize that, right? It's it's a secondary carbon, and there's no resonance or there's nothing else around really. So that one's just kind of, let's say, stuck, right? But for this top one here, we can do some kind of resonance stabilization, all right? So some kind of argument talking about resonance and stabilizing the positive charge. That's what I was looking for this one here. Okay. All right. So I will pick this up in the next video here. We'll start page 2 on the next video then.